energy and momentum methods for solving, for using forces to solve for accelerations, and therefore velocities and positions. There is nothing we can do from today's class that you couldn't have already done using force equals mass times acceleration, use your techniques from statics and physics, and proceeded from there. We're introducing these for one-dimensional situations first. So all of chapter 9, which is what we're doing now, is 1D problems. Now, one-dimensional problems with forces are actually quite dull. In one dimension, adding up and balancing forces is very easy. So, like for example, the textbook, someone would say, I'm applying a certain force to a 2 kilogram mass, and all you had to do is take that and divide by the mass to get the acceleration. So in one dimension, we're going to look at energy and momentum methods. And to start, I'm going to show you that we can get these energy momentum methods in one dimension by starting with F equals ma and repackaging it. So everything I'm doing today is just repackaging force equals mass times acceleration. You don't need any of this. But I think you'll see, what you've already seen in physics, is you use some of these energy methods, momentum methods, to solve some problems in physics 1. You found that there are some problems that are easier to do when you look at it from an energy perspective. It is also true that in nature, there might be something a little bit more fundamental about energy than there is about force. For example, a photon might have a certain amount of energy. When an electron jumps between two different energy levels, it emits a photon. It has that amount of energy. So being able to talk in terms of energy is a useful way to be able to converse as an engineer. So we are going to mention energy and momentum. So let me start with force equals mass times acceleration. And let me write the acceleration as dv dt. A little space there. And what I'm going to do might seem a little odd. I'm going to do something to both sides of this equation. And I think that you understand that if I did the same thing to both sides of the equation, I've not changed the equation at all. It's still a valid equation. Multiply both sides by 2. What I'm going to do is multiply both sides by a little teeny distance dx. Okay, so I'm multiplying both sides of the equation by dx. And then I'm going to integrate both sides. So I've done the same thing to both sides of the equation. On the left-hand side, I have the integral of f dx. And on the right-hand side, I can actually evaluate this more than you might think at first. I can combine this dv dt times dx. Like, you know, if you have 2/3 times 5, that's the same thing as 2 times 5/3. Dividing by 3, it doesn't matter if I attach the 3 to the 2 or I attach the 3 to the 5. This is a perfectly fine thing to do. So this is equal to m dv times dx dt. And when written that way, where I've slid the dt under the dx instead of under the dv, what can I combine to go on to the next step? Here I have a really ugly integral. It's got 2 differentials in it. It's got a dv and a dx in the same integral. In fact, and a dt. I have 3 differentials in the integral. I'm doomed. I can't possibly integrate that as it is. What can I do to kind of shrink this thing down a little? Get it down to size. Edgar, did you have a thought?
Well, dx over dt is v, right?
Yes. So how about we replace the dx dt with the v? And I will reverse the order, because I can do that because multiplication commutes, means the order doesn't matter. So I reverse the order from the v to the dv. Now I'm in a position to integrate this. So I'll integrate from x initial to x final, and v initial to v final. The mass is typically a constant. It's not changing throughout the problem, so we can pull that outside of the integral. And I get the integral of v dv. The integral of v to what? E squared over 2. I plug in my limits, and what do I get? We do all that in our head, or no?
B squared over 4.
So James says the integral of v dv is v squared over 2.
Yeah, so the f squared over 2 minus mvi squared over 2.
Good. Not because I have to, but because this is going to be a common clump of variables. I'm going to give that clump of variables a name. 1/2 mv squared. What name should I give that? Do you remember from physics? What did we call that? 1/2 mv squared. Kinetic energy. So I'll call this kinetic energy final minus kinetic energy initial. Or the change in kinetic energy. So the difference between the final and the initial would be the change in kinetic energy. On the left-hand side, I've got the integral of force with distance. The integral of force with distance from some initial distance to some final distance. This integral of f dx, we also give a name to it. So there, however, I can't evaluate it. If f is a constant, if I have a constant force, okay, then I can do something. I can pull the force outside, I can integrate dx and get x, but I can't do that for most problems. Force is not necessarily a constant. So for now, I'm just going to have to leave this, but I'll rename it. I'm going to call the integral of f dx by some new name to make this formula down here look really easy. James,
Is it a work?
yes. So the integral of f dx is what we call work. And I have this really simple equation. Work equals change in kinetic energy. So the total work done on an object equals its change in kinetic energy. Is there anything new I can get from this that I couldn't get from F equals ma? No, of course not. I got this equation from F equals ma. So I started with F equals ma, and I got it. What are the units of change in kinetic energy? Joules, correct. What are the units of work? Joules, has to be. Joules equals joules. Work, think of work as a transfer of energy. So if energy is transferred to an object, it's going to speed up. So its change in kinetic energy equals the work or the energy transferred to it. So there will be some problems where thinking in terms of this relationship will be easier than thinking from F equals ma. So we can save ourselves a little bit of effort. I'll do some examples in a moment. Before I do that, though, I'd like to start again with F equals ma, do something different to both sides of the equation, and get to a different version of it. So force equals m dv dt. This time, instead of multiplying both sides by dx, I'm going to multiply both sides of the equation by dt. So we'll multiply both sides by dt, and then I will integrate both sides of the equation. On the right-hand side, see if you can simplify it and integrate it on your own. Just take a moment, see if you can simplify and integrate that right-hand side. Okay, a lot of you canceled out the dt's. You brought the m outside of the integral. You got n times the integral of dv from v initial to v final. So we have m v final minus m v initial. On the left left-hand side, the integral of f dt. If force were a constant, which it usually isn't, if force were a constant, I could pull it outside, and I'd get f times the integral of dt. It won't normally work out that way, that force is a constant, so I can't do that, at least not, I can only do that for that specific problem. So I'll wait until I have a specific problem where force is a constant before I do that. For today, I'm just going to give this a new name. I'm going to give it some name and write that name here. I'm going to give these guys names, write their names down there. Mass times velocity has a name. Does anybody remember from physics what's mass times velocity? What? Momentum. But Roger, you're onto something there. Mass times velocity is momentum, so I can call this momentum final minus momentum initial. The symbol for momentum is a P. So this would be P final minus P initial, or change in momentum. On the left-hand side, the integral of f dt. The integral of f dt, we're going to give a name. The integral of f dt, the name we're going to give that is the impulse. Okay? So this is the impulse, and our symbol for impulse will be a J. Now, by now, you've taken enough science and engineering classes to start to understand why some of these symbols aren't as simple as you might like them to be. You now know, well, I couldn't have given momentum m, right? Because m is taken from mass, we have other problems. And you might think now, well, could I have given impulse an I? Well, those of you who have strength of materials, of course, we're using I for moment of inertia, capital I. I'm using lowercase I for a complex number. So I really am kind of out of ideas, so I'll just go to J for impulse. So J equals change in momentum. In chapter 9, which is where we're starting, we're looking at one-dimensional motion only. But let me just for a moment take a peek at chapter 10 where we're looking at multiple dimensional motion. Is momentum a vector? Yes. How do I know? Because mv is a scalar times a vector. Mass is a scalar, not a vector. A scalar times a vector will give me a vector. So mass times velocity has to be a vector. Therefore, momentum is a vector. Is impulse a vector? Yes. You can't ever have an equation where you have a vector equal to a non-vector. So if you have a vector on one side of the equation, the other side also has to be a vector. So you could have answered that question by saying, well, if that's a vector, that's a vector. Done. Or you could have come back here and said force is a vector times a scalar. Vector times a scalar is a vector. Well, what about the integral? Does maybe the integral change all that? Well, all an integral says is add together an infinite number of them. So add together an infinite number of vectors, and you get a vectors. So the integral isn't going to, by itself, change something from a vector to a non-vector. So here we have a vector equals a vector. How about over here? Well, we'll come back to here in just a moment. So if someone says, I have a momentum of 10 kilogram meters per second, it would be a reasonable question to say, in which direction? I could say east or something. It would be reasonable to ask somebody, in what direction is your momentum? Fine question. It is not a reasonable question to ask somebody, in what direction is your time? So James says, I've been sitting here for 4 hours. I say, in what direction? You know, that doesn't make any sense. So how about over here? Is energy and work, are they more like momentum or are they more like time? So if someone says there's been a change in kinetic energy of 10 joules, does it make sense to say, in which direction is that 10 joules? Does energy have direction to it? If you think yes, give me a thumbs up. If you think no, give me a thumbs up. Give me one guess one way or the other. I see some half thumbs, a couple up, a couple down. The correct answer is down. Energy does not have direction to it. So you can look at something like how much energy is stored in some chemical bonds. Somebody can ask the question, how much energy is stored in a gallon of gasoline? That would be a reasonable question without somebody saying, in what direction is the energy in my gas tank? I don't have to pick a direction. this is called a scalar. How about work?